Hello dear students, I welcome you back to my this video channel. I am Dr. Yusuf Hanif Sheikh, Associate Professor, Department of Physics, Shivaji College, Kannada. Today I am going to teach you wave particle duality part 3rd. In my today's lecture, I will be covering Davison's Germer experiment. In 1927, Davison and Germer in the United States and G.P. Thomson in England independently carried out a series of experiments on electron diffraction and confirmed the de Broglie's hypothesis. The experimental arrangement used by Davison and Germer is as shown in figure. Electrons from hot tungsten filament F are accelerated by a difference of potential between the filament F and plate P. The filament F and the plate P together are called as electron gun G. The electrons are emitted by thermionic emissions and are well collimated by suitable slits. This electron beam strikes normally on the surface of a nickel crystal. The electrons are scattered in all directions by the atoms in the crystals. The intensity of the scattered electron beam is measured by allowing the electrons to enter a Faraday's cylinder B called the collector, which is connected to a sensitive galvanometer. The Faraday cylinder is capable of rotation about a line in the face of the crystal through the point of incidence as an axis. The intensity of the scattered beam is measured as a function of the angle of scattering. The accelerating potentials were used from 40 to 68 volts. The results of one such set of experiments are as shown in the figure. When the potential difference between the F and P is 40 volt, the curve is fairly smooth as shown here. At 44 volt, a distinct spur appears on the curve at an angle of 60 degree. The length of this spur increases until it reaches a maximum at 54 at an angle of 50 degree. It then decreases and disappears completely at 68 volt. An electron accelerated with 54 volts at an angle of 50 degree is a typical case. This can be interpreted as being due to the constructive interference of the electron waves diffracted from the nickel crystal. This is exactly same way as X-rays are diffracted by Bragg's reflection from the regularly spaced atom of the crystal plane. As prominent reflections takes place at 50 degree, the angle of incidence and angle of reflection each must be 25 degree. That is to say that the reflecting planes in the crystals are inclined at 25 degree to the top surface of the crystal. As the lattice spacing for nickel is d is equal to the distance d between the reflecting planes, d is equal to 2.15 sine 25 degree, that is equal to 0.15 angstrom, that is d is equal to 0.915 angstrom. And the angle of incidence and scattering relative to the Bragg's planes is as shown in the figure will both be 65 degree. Now according to Bragg's relation, n lambda is equal to 2d sin theta. Here for first order n is equal to 1 and d is equal to 0.915 angstrom. So by substituting these values, we obtain lambda is equal to 2 into 0.915 into sine 65 degree. That is, its final answer is equal to 1.65 angstrom. So here lambda is equal to 1.65 angstrom. This is the wavelength that can be compared with the value obtained by substituting value of potential V is equal to 54 volt into the formula for de Broglie's wavelength. Lambda is equal to h upon mv, and h upon under root 2 meV. So its final answer we obtain is equal to 1.66 angstrom. Thus there is an excellent agreement between the measured value and the predicted wavelength. Thank you dear students for your patient listening. See you again in the next video. Till then, bye bye, take care.